Hi everyone, this is section 5.4, which is called Analyzing Graphs of Polynomial Functions. I'm going to ask that you have your graphing calculator with you as we go through this section so that you can do a few of the examples together with me and you'll understand the process of using your calculator. So the focus here is going to be using our calculator and kind of analyzing what we consider to be the zeros and the maximums and minimums of a polynomial function. So we've done this before with functions where we've actually used our graphing calculator in order to find the zeros. So we're going to kind of go into that a little bit further and talk about some of the other characteristics that also show up on our graph. So just to recap about things that we've talked about before, just remember that the zeros of a function are the values where the graph touches or crosses the horizontal axis. So we're looking for those places where, if I give you a graph down here, we're looking for those places where the graph is actually either passing through or touching the x-axis. So if I were to sketch something here for you, and I don't know the name of this function. We'll just call it y equals f of x right now. But I can tell from my graph that I have a 0 at whatever this x coordinate is. I have a 0 right here. I have a 0 right here. And then the graph is touching right here. And when the graph only touches the axis, this is the part in the notes that you should get down if you don't understand this already. The 0 is considered to be what we call a repeated root. And that means that if we were to look at the factored form of it, the factor that's associated with that root would show up more than one time. So it might be a power of 2 or a power of 4 or something like that. A lot of times in the things that we're going to look at, it may be called a double root because it would be showing up twice as a factor. So, excuse me, in this situation, we know that this function that I drew here has one root here, a second root here, a third root here, and then at a minimum 2 roots here. So I'm going to put roots 4 and 5. Now, this is an odd degree function, which means that the number of roots should be odd if all of them are real. And I can tell by the end behavior of this graph that because the end behavior is pointing in opposite directions, that my graph is not going to turn any longer, which means that all of the roots are drawn on our graph. So this would actually turn out to be a 5th degree function because we would have a total of 5 roots if that last root was considered to be a double root. If it was more than a double root, then it would jump to a 7th degree function, 9th degree function, so on and so forth. So you have to graphically be able to understand that a root can occur, or is 0. Remember, root and 0 can be used interchangeably. I've been using the word root right now. A root or a 0 can be found graphically by finding the place on the horizontal axis where that graph is either touching or crossing through. So make sure that you understand that definition. Of course, if there are any questions about it, bring those questions into class and we'll talk about it a little bit further. So as I move on to the next screen, I'm going to ask you to do the following with me on your calculator. Find the zeros of f of x equals negative x to the 4th plus x cubed plus 3x squared plus 2x. Now, here are some things that I know about this graph even before I put them into my calculator. I know that it's, excuse me, even degreed, and it's got a negative leading coefficient, which means that the end behavior is pointing down for both ends. So I know that as x approaches negative infinity, f of x will also approach negative infinity, and as x approaches positive infinity, our function will approach negative infinity as well. So the graph has end behavior that points downward. Now, it might look something like that. I also know that there could be a total of 4 real zeros. There don't have to be 4 real zeros, but it will have a maximum of 4 real zeros, which means our graph could touch the x, or pass through the x-axis 4 times it could pass through 2 times and then touch it once to make up the 4. And if there are any complex roots, it would touch in an even number of times or cross through in an even number of times. And then there would be 2 complex roots, because I mentioned in class that complex roots come together in conjugate pairs. So we're going to use our calculator. So pull that out to actually find these zeros. I'll pull mine up on the screen here if I can get to it. So under your y equals, I'm going to go to my large screen. I am going to type in negative x to the 4th plus x cubed plus 3x squared plus 2x. And I'm going to zoom 6 it just to see what kind of picture I get. Remember, that's our standard viewing window. I may have to adjust the window from time to time on some of these graphs, depending on what we actually see. So this is a pretty decent picture of things. I definitely see the height of the graph. I see the end behavior, how it would point down here. And I notice that the graph is crossing through the x-axis. It looks like right here and right here. So this tells me that even though I have a 4th degree function, there are only 2 real zeros, which means the other 2 zeros are going to be complex numbers. And I'm going to go through the process of finding these real zeros right now. So second calc, and choice number 2, remember 0 is the way that we're going to go about finding them. And I'm going to focus on this one here first. So I'm going to go a little bit to the left of where it is, which is below the x-axis. Hit enter. A little bit to the right, which would bring me above the x-axis. Hit enter again for that guess. And I get a solution of x equals 0. So one of my zeros will be x equals 0. As an intercept, it would be written as the 0.00, but when I name the zeros, I'm going to write them as x equals. The second 0, I'm going to go through this process again, second calc 2. And I'm going to curse over so that this time my cursor falls just above the x-axis. That will be to the left. Hit enter. Then curse below. Hit enter for the right bound. Hit enter one more time for the guess. And I find out that my second 0 is that x is approximately, and I'm going to approximate this one because it's a decimal, 2.512. I'm going to go out to 3 decimal places. Again, as an intercept, I would write 2.512 comma 0, but I'm concerned about the zeros. These are the 2 places where that graph is crossing the x-axis. Nowhere where it's touching, so I don't have a double root, and these are the only 2 real zeros of the function. Like I said, the other 2 would be complex zeros, and we'll get into that and finding those in another section later on in the chapter. So, you know, at a minimum, what you have to be able to figure out from this is how to use your calculator in order to find those zeros, and I think you're all pretty good with it. I've seen you work in class with it, so it may just be refreshing your memory and coming in with any small questions that you might have. So I'm going to go back to the notes sheet. And we found those zeros using the calculator, but what if we didn't have the calculator? What would we have to do in order to figure out where the zeros were? This is what I had to do way back when I was in school. We were kind of blind with this because we didn't have those calculators that gave us a nice visual. And what we would have to do is actually make a table. So if you don't have your calculator, or this is a question on an SAT or some type of standardized test, I would have to make an XY chart. And knowing what we know about the zeros, they'd be pretty hard to find. Not the first one, but the second one, which was a decimal. But the only thing I could do is kind of estimate, excuse me, where it would be. So I'm going to pick some values. Now, I'm choosing to start at -2 and kind of move on up, but there really isn't any rhyme or reason to what I'm actually picking. It's a little bit of trial and error to see what happens. If I sub negative 2 into my function, I would get negative 16, because negative 2 squared is 16, opposite of 16 is negative 16, minus 8 plus 12 minus 4, which gives us negative 16. So I would know that the point negative 2, negative 16 would be part of the graph. Right now, that means that the graph is below the x-axis. If I plug negative 1 in, I get negative 1 minus 1 plus 3 minus 2, which equals negative 1. So my graph is still below the x-axis. And what that's telling me is that I haven't found a 0 yet, because in order to find a 0 graphically, our table would have to, or through a tabular approach rather, our table would have to change sign for the y values. It would have to go from negative to positive or positive to negative to tell the person who's reading this that the graph actually passed through the x-axis. When I plug in 0, I get 0. That's a pretty easy substitution because they're all variables in there. This tells me, because I get 0, that x equals 0 is a 0 to the function. We're looking to get 0. If we don't, the best we can do with the table is to estimate where the 0 might actually end up. If I sub 1 in, I end up with negative 1 plus 1 plus 3 plus 2, which equals 5. So my graph has gone from a negative 1 here to 0 where it's crossing through, it's hitting the x-axis there, and then it actually passes through because the value becomes positive. I'm going to try 2, excuse me, and when I plug 2 in, I get negative 16 plus 8 plus 12 plus 4, which gives me 8, which means my graph is still on the rise. It hasn't made a turn, and I'm not finding another 0 yet. Then I go to 3, and I'll get negative 81 plus 27 plus 27 plus 6, which gives me a value of negative 21. So now what this tells me is that somewhere between the x values of 2 and 3, there's a 0. Table-wise, I can't get really any more specific than this unless I started testing values that are decimal oriented between 2 and 3 to try to pin it down a little bit more. But by the decimal that you saw us get, 2.512, it would be pretty hard for me to get it exact. So if you don't have a calculator, the table approach is the way that you would do it, but it's not the best because you're probably not going to get all of the zeros. And in all honesty, I wouldn't even know if I had all of them. Now, what we saw graphically was that there were only 2 real zeros. I found the 2 real zeros in this table, but if I didn't have any knowledge of that picture beforehand, I wouldn't know if I was still looking for other ones. And I'd have to test more values to kind of get an idea of how the graph was acting in order to figure that out. So again, you guys are lucky because you have these calculators, and I'm going to ask you to use them as an aid to help you do all of this, rather than just be kind of blind as you go through it and doing like a guess and check. But you should know how to estimate if you had to. So the next piece, lots of definitions in here that we want to talk about are maximum and minimum values. And we've talked about this before. You've talked about it in Algebra 1 even, about what a maximum or a minimum means. And remember, a maximum occurs when a graph, first of all, our function f of x, it's going to increase, so it goes up, and then decrease and goes down. So we know when that happens, our graph actually makes a turn, and when it makes that turn, it reaches a maximum. That maximum is considered to be what we call a relative maximum, where that change occurs. So depending on how we're going to provide, the context of our answer, we may provide the actual point, the ordered pair, coordinates of x comma y for that actual maximum point, or we might say the y value is the maximum value on the graph. So that will vary depending on the scenario that we're in. But what you need to know is that it's called a relative maximum. If for some reason that relative maximum is the absolute highest point on the graph, so it's the absolute largest range value that occurs, then that relative maximum turns into what we call an absolute maximum, because there will be no higher ordered pair or y coordinate on that graph. Not too hard to understand. You just have to make everything is considered relative. only some values will be considered absolute because they'll be high points, absolute high points on the graph. Now, the reverse holds true for a function f of x if it decreases, so it goes down, and then it increases and goes up. We have then what we consider to be a relative minimum at the point where that occurs. So we're seeing something that would look like that, and we would have a minimum value. If that relative minimum, of course, contains the absolute smallest range value, then we would classify it as an absolute minimum. So part of your job is going to be classifying the minimums and maximums that you get. We call these values together extrema values, and you may want to make a note of that up top, that they can be classified together as extrema values, and that means that we're talking about either maximums or minimums. So we're going to do some of that together in an example so that you can see what the expectations will be. So I'll move on to the next screen. This is another one where eventually you're going to want to have your calculator when we do the example. Now, one other definition is a turning point. And the point where the graph actually makes the change in direction. So where the point where a graph changes direction, either from increasing to decreasing or decreasing to increasing. We call that point a turning point. So the maximum or the minimum value is considered to be a turning point. A polynomial function has n minus 1 turning points, where n is the degree of f of x. That means that if I gave you f of x equals x to the 5th minus 6x squared plus 7, we have at most 4 turning points in this graph. Now I say at most because it doesn't have to have 4, but it will have at most 4 turning points. It's always one value lower than what the degree is. So you might be asked about the number of turning points. The number of turning points on a graph, if we know, can see it, then we know what the degree is of the function, if we know that the graph is complete. The next question I want to ask you is this one that's on the screen. Do all functions have an absolute maximum or a minimum? Think about that for a second. Will every single function have an absolute maximum or a minimum? So we said an absolute maximum or a minimum occurs when we have an absolute greatest y value or smallest y value occurring on a graph. Will every single function have an absolute maximum or minimum? I want you to think about that for a second. Maybe sketch something that would or wouldn't prove this. Now, I'm thinking this. We have 2 types of functions, basically even degree and odd degree. If we have an even degree function, then that means that the end behavior points in the same direction. So my graph might look like this. This is the most basic even degree function. Or like this. Again, most basic even degree function. In both of these scenarios, I have a minimum in the first, a maximum in the second. Both of those values are absolute extrema values because there is no value lower in this one or no value higher in that one on the graph of the function. So when our graph is even degreed, it seems that we have absolutes. Now what about our odd degree functions? What do we know about odd degree functions and their end behavior? Something that's considered to be odd degree might look like this. Now, in this odd degree function, this would be a cubic function. We know the graph is complete because I see the arrows on the ends. I have two situations where I have extrema. One is right here and one is right here. So I have a relative max at this point right here, and I have a relative min at this point right here. But could I classify them as absolute? Your thoughts should lead you towards the answer of no, because this relative max leads you to this y value, but you notice that there are other range values that are higher on that graph. And the same is occurring for this relative min. There are still range values that are smaller than that. So an odd degree has no absolute extrema. And you should start to make those connections with the graphs that we look at so that you can classify and analyze some of them. Let me know if you have any questions about anything that I talked about on this screen when you come into class next time. So we have a couple things left here. This one example says graph the following function on your calculator. So we're going to do that together. Then find the real zeros and any maximum or minimum values. Classify them as relative or absolute. So let's see what we can even do before we reach our calculator, because it would be awesome if we could just have a conversation about the function first. We know that this is odd degree. We know that it has a leading coefficient of 2. So the end behavior will act like this. I'm not even drawing the coordinate plane on there, but we know that the end behavior will be in opposite directions, and it's considered to be an increasing function because as we trace it, it's always going up. Even though there's a little dip here, the overall idea is that the function increases. So we should be able to conclude from our graph that there will be no absolute extrema. We know that the graph might turn at most twice because we go one value lower than the degree. So we might have 2 turning points, and we might have a total of 3 zeros because the degree is 3. We're either going to have 3 zeros that show up on the picture or 1 zero, because if we had any complex zeros, they come in pairs. So if we had a complex 0, we would automatically have another one, which would leave us with only one spot where the graph could cross the x-axis, and it would have to cross. It wouldn't be able to touch at that point in time. So let's take a peek and see what this graph looks like. All right, so we're going to throw in 2x cubed plus x squared minus 4x minus 2. Zoom 6 to see what kind of picture we get. See if we have to adjust the window at all. And it looks like we see a pretty good graph. I might actually do this just to play around with it and show you how we can adjust a little bit. I might change my x-axis to go -5 to +5 to bring it in a little bit more and get a better view horizontally of it. So what I see is this. I do see my end behavior going in opposite directions, which mimics that odd function. I do see 1, 2, 3 real zeros. So that means we have no complex zeros. We have as many real zeros as the degree. And I see a total of 2 extrema values. One is here and one is here, which implies that we have 2 turning points. Now, the directions are asking us to actually find the zeros and the extrema. So I'm going to go through the process of finding the zeros, second calc 2. I'm going to do the leftmost one first, this one right here. So I will curse below, that's where the left bound will be. So I'm going to look until my y values are negative, hit enter. Go now till my y values are positive, hit enter, because that means I crossed over and are to the right of the 0. Hit enter for guess, and I'm getting x is approximately -1.414. That's actually, I know off the top of my head, the opposite of the square root of 2, to be exact. But you guys can give me the decimal, that's perfectly fine. The second 0, second calc 2, is going to be this 0 right here. So my y value is above the positive and is above there, so I'll hit enter. I'll go below. I could have went one closer, 2 closer. So now I'm below. Hit enter, and I get x equals -0.5. And I'll keep it in decimal form because the other one was written as a decimal. If I had it exact and I wrote -√2, I would write -1/2 probably. And the third 0 is going to be second calc 2. It's going to be this one over here. So I'm going to go close. My y value has to be negative to be left. That looks pretty good. When I hit it again, it becomes positive, which means I move to the right, hit enter for the guess, and x is approximately 1.1 or 414, which I know is the positive square root of 2. So those are my zeros. You notice I use the approximate sign when I round my decimals. I'm going to go to 3 decimal places at all times if I'm rounding. And then my max and my mins. I don't know how much work you've done with this before. We may have touched on it in class. Second calc is going to bring us back to that screen. And I have minimum and maximum, choice 3 and choice 4 here. Minimum is going to be for my minimum. Maximum is going to be for my maximum. So I'm going to choose, I think the maximum was first on the left, choose number 4. And I'm going to curse over to, it asks for a left bound, so I'm going to go a little bit left of where the maximum is. You don't have to be far away from it. Hit enter. Go a little bit to the right for the right bound. Hit enter. And then I'm going to hit enter one more time. And it's going to tell me that the max is going to be at the point -1, 1. Now this is only a relative max because there are other y values on that graph that are higher than the y coordinate of 1. I'm going to do the same for the minimum. Second calc 3 this time. I'm going to curse a little bit to the left of where the minimum is. Hit enter. A little bit to the right. Hit enter and then enter one more time for the guess. And I see that the minimum is at 0.667. If I was going decimals, or fractions rather, that would be probably 2/3, comma, -3.630 if I round properly. So I'd have to stick with decimals there because I don't have a fraction equivalent of that. This again is just going to be relative because there are other values on the range on the y-axis that are smaller than -3.630. So you have to be able to use your technology in order to figure out these values. Back in the old day, like I said, I had to do this longhand, which was a real pain in the neck. But the fact that you have your technology does help. So again, if you didn't have your calculator, to find the max and the mins, you'd have to look for where the graph increased and then all of a sudden started to decrease again. So that's the idea of using your calculator for that. I'm going to go back to the screen here. And it kind of fulfilled what we thought, what we talked about before. There were 2 turning points. We had 3 real zeros. The max and the mins were both relative. There were no absolute. So it held true with what we found when we just had a discussion about what the function looks like. And those are the things you should run through in your head, is think about what you know about the function before you even get to your calculator, and then confirm what you thought you knew via your calculator. This last problem is kind of the reverse. I'm going to give you some characteristics, and I want you to come up with a graph that would fit all of this information. So I'm asking you to sketch a graph of a polynomial function that has the following characteristics. It's got to be 5th degree. So that means that we would have at most 4 turning points, zeros at -4, -1, and 3, and a max at x equals -2. Now, I'm going to tell you right off the bat, there are various ways that this could be done. My way is not going to be the only way. So let's draw a coordinate plane. And what we know is this. We know that we have zeros at -4, -1, and 3. So I'm going to put some tick marks on my coordinate plane. Now, I'm going to assume that these are zeros that are listed, but they may not be the only zeros. We know we have a max at -2 and zeros at these points. So I'm going to put at -4, place where the graph hits the x-axis, -1 and then positive 3. And then I am going to put a maximum at x equals negative 2. So I'm going to go up, and this is going to be my maximum. Now, if it's 5th degree, it's only a relative maximum. So somehow I have to fit this information in. In order for it to be 5th degree, I could have my graph do something like this. It could go pass through my first 0, go up to my max, reach my second 0. Sorry, this isn't perfect here. Go here and turn but not touch, which means I would have a complex and then pass through the other 0. Let's see if that would work. How many turning points do we have? We have 1, 2, 3, 4, which means we could have a 5th degree function with that. We have the 3 real zeros right there, and we have our maximum at x equals negative 2. Now, this other place where we have a maximum right here, I should do that over in blue, is perfectly fine because I fit the turning points to match the degree. And what this means is that there are 3 real zeros, but the other 2 zeros, if this were 5th degree, would be complex zeros, which means that we get those zeros from some other way than looking at where the graph touches or crosses the x-axis. I could have brought that up, I suppose, to touch the x-axis, which would be a double root, but since there wasn't a real number listed, I avoided that. So like I said, excuse me, there are various interpretations to this. This is just one, but you will do some problems where you have to kind of be creative and think about what the characteristics are asking you to graph in the exercises that I'll give you. So in a nutshell, what we talked about here was making sure that we can find the real zeros on our calculator, making sure that we can classify maximums and minimums, identify those on our calculator, find those on our calculator, and classify them as absolute or relative, and then sketch a graph of something that would fit certain characteristics that were given, like the degree, the zeros, maximums, maybe even turning points or something like that. So make sure that you come into class with any questions that you might have. We'll run through those questions and then do some problems that deal with this type of information. So thank you for listening, and I will see you in class next time.